Did I say that we don't learn MAC addresses on Ingress? You do learn MAC addresses on Ingress, but only on ports that are in the forwarding state. So if I receive a packet in and it comes in on a blocked link, I don't learn the MAC address on that particular port. You're only allowed to put MAC addresses in the CAM table if the traffic was received in on a forwarding port. So essentially what Spanning Tree is doing is just telling the switch, when traffic comes in, how do you build the layer 2 switching table? If a packet comes in on this port that's forwarding, you can learn. If a packet comes in on this interface that is blocking, you have to drop it. Okay, there was another question. I guess the root primary and the root secondary commands still work. Yes, they do. So same exact logic as you have in Catalyst. You could go to global config and we could say, for Spanning Tree VLAN 20, I want to be the root and I want to be the primary root. Basically, the only thing this command is doing is it's a macro that picks a low priority value for you and then it puts it into the global config. So when we look at the result of this, if we show run pipe include Spanning Tree, the end result is that it's just configuring a lower priority, lower than 32.768, which is the default value. So if I was to go to another switch, let's say 5K7, and issue the same exact command, and we show run pipe include Spanning Tree, it changes my value to lower than theirs, and actually we already have a lower MAC address. So if we look at the show Spanning Tree for VLAN 20, I am the root. If we went to the other switch and did this again, it would continue to lower the priority value. But one thing to note about this is that if you use the root primary or if you use the root secondary command, it is not actively tracking the state of who currently has the root bridge status. So right now we can see that this switch configured its priority as 20,480. There's nothing stopping me from going to another switch and configuring it as 8192 or as 4096, and then basically stealing the root status away from this particular bridge. So the only thing it's doing is that you don't need to manually remember who has which number. You just set the root primary on whoever you want to be the root. It looks at the current topology and then sets its own root bridge priority, or sets its own priority lower than whoever the current root bridge is. There's a question, can I explain the nominal bit rate again? What the nominal bit rate is it accounts for the layer 1 framing of the interface. So this interface here is 1000 base T. And I don't know offhand exactly what the encoding is, but it's different per specification in terms of when you send Ethernet over copper versus Ethernet over single mode or multi-mode fiber. The layer 1 framing is different between the two of those. So if you look for the 1000 base T encoding, the physical coding sublayer. So basically what this would show you is what do you need to add in the physical link in order to send the packets over the medium. But this data that you're putting is actually in the layer 1 frame. So if you capture it bit by bit and you look at the length of the frame, the effective bandwidth that you can use for data is 1 gig, but there's additional bits on the frame on top of that in order to deal with like the layer 1 clocking of the link, to make sure that when I send a packet, you're ready to receive it on the other side. So normally you don't really need to get involved with that, what specifically is going on with the encoding. But what it would affect is that if I'm running 1000 base T on the other side, and then, or excuse me, if I'm running 1000 base T on this side, and I try to go to multi-mode fiber, or I try to go to single mode fiber on the other end, then it's not going to work because they have different layer 1 encodings. So same is true with the 10 gig Ethernet. If you plug a multi-mode fiber into a single mode fiber, beyond the wavelengths that they're using, even if they were using the same wavelengths, you wouldn't be able to receive the traffic. because it uses a different physical encoding at layer 1. But what this shows us from our point of view is what type of transceiver is it. So if you look at the show interface E132 transceiver and the show interface E110, and let me parse this a little bit. Let's say pipe include bit rate. And then the E11. This one here is 10 gig E. This one here is 2 gig fiber channel. This one here is 1 gig Ethernet. And as somebody had mentioned here, specifically what they are is it's 64B, 66B for 10 gig E. It's 8B, 10B for 1 gig, which affects what the overhead is. So it's basically, if you don't have compatible transceivers, you're not able to do the layer 1 negotiation on the link, and the link status would be down. But the reason this is important, if you look at physically, if you look at the SFP, it's easy to confuse one for the other. So if we look at the, let's say, Cisco 2 gigabit fiber channel SFP, and let's open up a picture of that, and then we were to look at, let's say, 10 gig multi-mode SFP, when you look at these physically, they look identical. And also the cabling is the same. So your same multi-mode fiber that you're using for 10 gig E, it's going to fit in the fiber channel SFP. So if someone plugs the wrong one into the port, the layer 1 status is not going to come up because it's using different framing. And the way that you can troubleshoot that, other than pulling the SFP and looking at the actual wording on it, and you can kind of see here it says FC2, but not all of the SFPs say that. They might be like just off-brand ones that have like the manufacturer's name on it, and you won't actually know until you plug it in and look at how the switch recognizes it to see what is the actual layer 1 framing format that it's using. There's a question, does the nominal bitrate indicate the end-to-end throughput? It means the maximum throughput on the link, but it's the maximum throughput including layer 1 encoding. So your effective throughput, like if you have a web server or like a file server and then a client, and you download a file over TCP, you're not going to get 1300 megabits per second effective throughput on the 1 gig link. Your effective throughput is 1 gig, it's just that on each of those packets that you send, there's additional layer 1 encoding that the physical SFP needs to do before it encapsulates it on the wire. But it is kind of a common mistake for someone to make it layer 1. So that's why it's important to notice here that when you look at this and see SFP invalid, it doesn't necessarily mean there's a layer 1 problem. It could mean that the speed is not properly negotiated, or it could mean that they plugged an Ethernet SFP into a fiber channel port, or vice versa.